5 of our 6-week webinar. The topic of this week is Step 6, Multivariate Analysis. I'm William Bannon of Stats Whisper, bringing you the presentation today. As always, we like to keep in mind where we are in our 7-step process of data analysis. And here we are, Step 6, Multivariate Analysis, getting pretty far down the line, right? So this is a big week for us with a lot of answers. So if we break up the term multivariate analysis, we know that multi means many, and var means variable, so we can infer that it's an analysis between many variables. Right? Specifically, it's an analysis that involves many predictors, right? So, more than one covariate variable or independent variable being related to the dependent variable. For example, if you recall Study 1, Sample Study 1, on the left-hand side, we have several predictors, right? Several predictors being related to the one dependent variable on the right, which is happiness. Now, last week, in bivariate analysis, we used 3 separate tests to test that model. Right? So we used an ANOVA, one-way ANOVA, to see if education level was related to happiness. We used a correlation, our second test of correlation, to see if income level was related to happiness. And third, we used a t-test to see if living with a dog or a cat was related to happiness. So 3 separate tests to test this model. But this week, it's another story, right? So the multivariate analysis will test this model with one test, right? So on the left, again, multiple predictors, right? We have 2 covariates, 1 independent variable, and they're being tested at the same time by multiple linear regression. So on each arm, we have multiple linear regression, right, being tested with happiness. Now, the difference between linear regression and multiple linear regression, we want to say this early because you might have heard both terms used. Linear regression generally refers to one predictor and one dependent variable. So multiple linear regression usually refers to multiple predictors being regressed upon the dependent variable. So as I said, the multivariate analysis is going to answer some big questions for us. Right? So what is the final statistical significance between the covariate and independent variables with the dependent variable? So when I say final, that means the final level of statistical significance that we'll report in our study as the finding. Right? So earlier we had bivariate findings, but we're not going to report those as the conclusion of our study. Right? Those were building up to this point. So in the regression model, the levels of statistical significance between the predictors and the dependent variable are the final levels that we'll report as our findings. Right? So what variables are significantly related? Right? So like I said, this is what we're going to use to determine what relationships we consider in N to be significantly related. Next, we're going to look at which predictor has the strongest relationship with the dependent variable. And we can see this because we'll be testing the influence of all the predictors at the same time upon the dependent variable. So we'll see which is the strongest, but also we'll see the impact, right? So the effect side, the impact that each predictor has on the dependent variable in the context of the full model, which is a key term, the context of the full model. And so those, again, are the final findings that we'll present as the findings for our study. So how many tests do you need? Right? How many tests do you need to do multivariate analysis? Well, the first thing is, you see little asterisks there. This refers to cross-sectional analysis, not longitudinal. But in cross-sectional analysis, there's generally three regression models, three types of regression that can be used to test the multivariate relationships. We used linear regression and binary logistic regression, two. And then third, multinomial logistic regression, which we won't get into today, but we want to mention it, for somewhere down the road. Now, how do you choose the right one? Again, just like in bivariate analysis, how do you choose the right one? You look at the variable structure, right? So you look at the structure of the variable, the structure of the dependent variable specifically. So again, we consider the same three structures as we mentioned in bivariate analysis. One, the continuous variable, such as, happiness on a scale of 1 to 5. Two, we consider the categorical variable with two categories, such as happy, yes or no. And then three, the other structure for the multinomial logistic regression would be three or more categories, such as yes, no, somewhat. So we could turn this into a multivariate test key, just like we had the bivariate and the univariate test key. Right? So the first line, continuous dependent variable, linear regression. The next line, a categorical dependent variable with two categories, binary logistic regression. And again, the multinomial logistic regression with three or more categories. Now, if we plug in, right, so sample study 1, right, we see in the italics here, sample study 1 involves a dependent variable which is measured on a scale of 1 to 5, a continuous scale. Therefore, we would select a linear regression for sample study 1, right? So it really breaks down kind of simply if you can get these bare facts, right? So if you have these facts, it's actually not too difficult to determine what test you need. And as we'll show next, it's also not too complicated to actually conduct and interpret the test. So remember, the term linear regression, I want to discuss this a little bit first, because what exactly does it mean? It's not terribly intuitive, right? But so it's going to tell us if there's a significant linear relationship between the dependent variable, such as happiness, with the covariate and independent variables. But what does that mean? Right? So recall the correlation. Right? So this is very similar to the correlation that we used in bivariate analysis. So specifically, you could look here. Happiness is on the horizontal axis, and income is on the vertical. Right? So you can see here the cases. So suppose these are cases. So case 1, all the way to the left, you could see they got a score of 1 for happiness, the lowest level of happiness. They also, in terms of income, let's say for the income axis, 1, 2, 3, 4, 5 is hundreds of thousands of dollars. So the 1 is $100,000, right? So the income of $100,000 is associated with 1, the lowest score of happiness. But then you see for happiness with a score of 2, that dot intersects with the 2 for the $200,000. Then the happiness score of 3, right? That score intersects with the vertical axis, 3, for $300,000. The same with 4 and 5. So up at the top, for happiness 5, with the highest level of happiness, there's also income 5, $500,000, with the highest level of income. So you would say as happiness goes up, as income goes up, the level of happiness goes up. So if you got rid of where it says case, you could actually say that these dots form a line, right? So we superimpose this dotted line here to illustrate our point, right? So this is called the regression line. So it's linear regression because the cases regress one after the other along this line, right? So 5 meets 5, you regress 1, 4 meets 4, you regress 1, 3 meets 3, you regress 1, 2 meets 2, right? So they're all regressing together along this line, right? So it's linear regression. And so that's what we're testing for. Now, very essential fact here. When we're doing a regression model, and this could be linear regression, binary logistic, and the multinomial also, when you have a predictor, an independent variable or covariate variable that's categorical, but it has more than 2 categories, you need to dummy code that variable. In other words, all the predictors in the regression model have to be either dichotomous or continuous. So if we have a categorical predictor that has more than 2 categories, meaning it's not dichotomous because it has more than 2 categories, we need to break each category within the variable down to be a separate dichotomous variable. And we're going to use education level to illustrate our point. So in our text, this is on page 204 to 212, right? It'll tell you how to dummy code the variables, but we won't go into the nuts and bolts of how to do it here. We'll just conceptually discuss it. Okay, so the dummy coding turns the single categorical variable with more than 2 categories into the several yes-no variables. That's what dummy coding means. So consider the variable education level. It is one variable, categorical, with a 3-category response. So the study participant can either answer high school GED, or they could say college, or they could say graduate school, right? But we can't use the variable in that form in the regression model. So we use dummy coding, and via dummy coding, the education level variable becomes 3 dichotomous variables. So you get 3 for the price of 1. Right? So you have now 3 dichotomous variables. So variable 1 becomes, is education level high school, yes, no. Variable 2, education college, yes, no. And variable 3, education graduate school, yes, no. So the variable is now dummy coded into 3 smaller variables. Now, important point. When using it in the regression model, you have to actually exclude one of the categories to make them the reference group. So one of these groups, variable 1, 2, or 3, is left out of the multiple regression model. So it's excluded from the regression model, and the findings of the other 2 variables that are included are interpreted in reference to the reference group, which is left out. Now that's slightly less confusing when we actually do it in the model. So if it doesn't make sense right away, that's okay. It'll make sense soon. But just keep in mind, we're going to have to select one as the reference group. And there are many criteria for selecting a reference group. For example, if one group, if the study was on people with a high school level education, then we might leave them out and they would be the reference group because we want to know how the findings come out in terms of their outcomes. Right? One example. Right, now, of course, I'm going to reiterate, for the categorical variables that are already dichotomous, such as do you live with a dog or a cat, you don't have to do any transformations. They're fine as they are. we do linear regression in SPSS, we go to Analyze, Regression Linear. We're going to put the dependent variable in the dependent box, and the covariate variable is an independent variable in the independence box. And if you didn't do your collinearity checks, remember to click that box. Then we'll click OK or Paste. Paste being the smarter option. All right, so let's do that right now in our SPSS. So break that down. So here we go. We'll analyze regression and linear, as promised, right here. So we have happiness. Let's take these out so we could put them in one at a time. Okay, so first, remember we said we had to leave one group out, our reference group. Let's say we left out high school, and we put in the dummy code for college and graduate school. We put in income, and we put in living with a dog or a cat. Then we could click it, or we could paste it. Pasting it's nice. Right there we could save our syntax, and we can run it, and then we come up with our output. Let's go back here since we have the output presented. Okay. Now, in the regression printout, in the output, the first thing you'll see, well, a few boxes down, but the first thing you want to note is the ANOVA box. So there's a small box, and it says ANOVA, and to the last column on the right, it says SIG. Now, this is important because this is the level of statistical significance for the entire model. And so if this isn't 0.05 or below, right, as in statistically significant 0.05 or below, then the entire model is not credible, and we don't consider anything else. Right? However, we can see here that our significance level is 0.000, which means that it's a statistically significant linear regression model. And of course, you can call it a multiple linear regression model because we have more than one predictor. Okay, the next thing we want to look at below that box is there's the coefficients box. So this tells us about the individual predictors. Right? So that told us about the whole model. This tells us about the individual predictors within that model. Okay? So the first thing we want to know is, are any of the predictors statistically significant? If the model is statistically significant, but there's no significant predictors, that really doesn't tell us much. So you look at the last column, which also says SIG, and you can see at the end of each predictor, there's a p-value, right? So you can see for this model, all of them are statistically significant, right? So all the variables are significantly related to happiness. Okay, now remember, when we look at education and college, right? So that's our dummy-coded variable. So when we look at education college and it's significant, it's not a direct relationship. So it's not that college is associated with more happiness, right? There's the reference group. So what it's saying is that in reference to people that with a high school level education, those with a college level education have a significant higher level of happiness. Right? So it's interpreted differently than the non-dummy coded items. Right? So the same thing with graduate school, right? So those that attended graduate school have a significantly different level of happiness in reference to those with a high school level education. Right? And the same thing with income. There's a significant relationship between income and happiness. And there's also a significant relationship between living with a dog or a cat and your level of happiness. So we know the relationships are significant, but that's all we know right now. So let's consider our next topic. So we want to know the directionality. So essentially, the directionality, the unstandardized beta, which is highlighted here, as well as the standardized beta coefficient, if there's a minus in front of the coefficient, we know it's a negative relationship. If there's no minus, we know it's a positive relationship, right? So for example, college, education college, there's no minus, so it's a positive relationship. So positive meaning more. So what it's saying is those with a college level education have significantly more, right, a higher level of happiness in reference to those with a high school level education. The same finding for the graduate school education. Also, we see for income level, there's no minus, so that means as income goes up, right, there's more, because there's no minus, it's positive, happiness goes up. However, the dog and the cat, right, there's a minus there. Now, this depends on the coding. You have to know the coding of the dog and cat variable in order to effectively interpret the finding. So we know dog is coded as 1 in the SPSS database, right? Remember, you go under values and all that. So dog is coded as 1 and cat is coded as 2. That means as the variable goes from 1 to 2, as it increases from 1 to 2, there's a minus. So happiness goes down. As the dog and cat go up from 1 to 2, the level of happiness goes down because there's a minus. So that means that living with a cat, right, going from dog to cat is 1 to 2, so living with a cat is associated with a lower level of happiness. All right, next, the standardized coefficient beta, right? So this will tell us the strongest predictor in the model. So the higher, so it doesn't matter if it's minus or positive, but the higher the standard coefficient beta, you know, the more powerful the predictor. And we can see here that income is the strongest predictor with the standard coefficient beta of 0.386, but all of them are hovering around that, you know, 0.3 area, although income is higher, right? So our independent variable is 0.306. So it's not the lowest, right? The lowest is 0.252, which is, you know, the college category, and it's not the highest like income, but yes, it's pretty, so it's the mid-range. Now the next thing we want to look at is another effect size estimate. It's the R squared. So the R squared is in the output, and it tells us how much variance, right? So variance just meaning scores going up and down. So how much variance in happiness, so what makes the happiness scores go up and down? That's what we want to know, right? That's what we're trying to explain. What makes you happy and less happy? What makes it go up and go down? So the R squared tells you all the predictors in the model, how much of the variance in happiness do the predictors explain? So R squared is 0.489, which is almost which is a percentage. So that's almost 50%. So let's say 49%. So what this is indicating is that 49% of the variance in happiness is explained by our predictors in our regression model. So these three variables explain 50% of, or half of what makes, you know, happiness scores vary, going up and down. So that's actually a really, really, really big effect size, especially for just three variables. So usually you'll see that on the smaller end. Sometimes it's just 0.06, 0.10, 0.20, 0.30 is even high, right? So the adjusted R-squared is the computer's way of saying we know this isn't the actual effect size in the population, but if we were to estimate what the effect size in the population is, that's the adjusted R-squared, so 43%. So, of course, the closer the R-squared and adjusted R-squared are, like the more similar they are, the more believable or the more credible the number is, right? So there's a little difference in between, these two numbers. So you want to take that into consideration. Okay, also, as we always say, we like to look at the effect size of the predictors. And on page 219, one of the ways to do that in our regression model is put it in the ANCOVA function, right? So we put all the same predictors in the ANCOVA function, and it produces the partial eta squared, right? So the partial eta squared produced is 0.092. So that's certainly not the biggest because income is 0.646, which is tremendously high, right? But we could see that the living with a dog or a cat, right, has a medium to large effect size on your level of happiness. So if we roll it all together, here's what we have. Our multivariate model indicated, now here we go, here's where it sounds all scientific-y, that while controlling for education and income level, living with a dog or a cat is related to happiness, where those living with a dog are significantly happier than those living with a cat at a statistically significant level with a medium to large effect size. Right? So think about everything we've done at this point, from data entry to checks of data integrity, all of it just to produce this one sentence. Right? But it's solid now. See, that's a good thing. Behind this one sentence is just a tremendous amount of work, right? But it's a solid finding because of that. Now you see the little yellow boxes on the left. They're pointing out the 3 dimensions of a relationship, right? So the first one on the top says D2. That's our directionality. So that's the dimension of directionality, where those living with a dog are happier, and that's the directionality of happiness. 1, statistically significant, the next box underneath, so we know it's significant. And then 3, we have our effect size, which is medium to large. And so all bases covered. Now, let's consider the multivariate model for sample study 2. This is even more fun because it produces, you'll get to see down the road here, the odds ratio, which is one of the most universally understood effect sizes, not only in science, but outside of science. I mean, when you hear news reports and they say twice as likely, people understand that. So sample study 2 is very valuable to us because it's very understandable to, to most people. So recall, sample study 2 is almost the same as 1, but the dependent variable has been dichotomized. So instead of happiness 1 to 5, we're talking about either you're happy yes or you're happy no. So it's a dichotomous dependent variable. So if we look at our multivariate test key, we see if we have a categorical variable with 2 categories, in other words, dichotomous, we use binary logistic regression. And if we plug in our dependent variable, see it's italicized there, we have happy, yes, no, and binary logistic regression. So that's our way to go. So in general, what the binary logistic regression will tell us is a significant relationship between our categorical dependent variable, and the covariate and independent variable. More specifically, are the study participants who live with a dog significantly more likely, and it's a term used with binary logistic regression or logistic regression in general, more likely to be happy, yes or no, relative to those that live with cats? So this is almost a little more definitive, right? So it's not just higher or lower scores for happiness, it's being happy, yeah, happy, no. It's kind of more definitive, black and white like. Okay. So for the binary logistic regression in SPSS, binary, again, and the dependent box, the indivariate variable, and the covariate box, again, remember to leave out the reference group. Also under options, always click, right, point 4 here, always click the 95% confidence interval. You'll need to report that. And then it's just continue and OK, or paste to those with the more conservative approach. All right, so if we go to SPSS, right, it's pretty easy. Just analyze, regression, binary logistic, and there we go. So we put our happy yes, no here, then our independent and covariates here. Now here's what I wanted to show you. Under options, always click right here, the 95% confidence interval, and you'll see those reported in our slides. So here we go. So kind of like the regression model, the first thing, the linear regression model rather, we want to look at is the entire model statistically significant, right? And so coefficients. That's what you want to look at, and again, it's the final column labeled SIG. You can see here that in the last line where it says model, the significance level, this is the p-value, is way below 0.05, 0.000, which means the binary logistic model is statistically significant, right? And again, if it wasn't, you wouldn't consider anything else within the model, because the whole model would not be credible. So the model significance, so we move on to our next consideration, which is the significance level, the p-value of the individual predictors. Now what's really interesting here is you'll see the statistical findings are actually a little different based on when happiness was continuous rather than when it's now categorical. And so the relationships between the variables change depending on the structure of the dependent variable, even when it's the same scores. And so what's the truth? And so that's what I mean. You have to consider, well, we see high school, like education high school is again left out. So that's the reference group. But when you look at education college under SIG, that's the first p-value. The p-value is 0.732. So that means that those with the college level education are not significantly more likely to be happy in reference to those with a high school level education. And so it changed the findings. Then the next p-value is 0.000. That's grad school. So what that's saying is that those with the graduate school level education are significantly more likely to be happy, yes, right? Yes, no, to be happy, yes, in reference to those with the high school level education. Right? And then the same thing with income level. There's a 0.003. So income is still significantly related to being happy, yes. And living with a dog or a cat is also significantly related to being happy, yes. Right? So they're all still significant except for education, college. Then the beta, we'll see that the beta and the odds ratio both reflect if there's a significantly positive or negative relationship. But here the beta, just like in linear regression, if there's a minus, it's a negative relationship. If there's no minus, it's a positive relationship. So we can see the same trend as in linear regression, where they're all positive relationships, except for the dog or cat variable, which is a negative relationship. And again, you have to consider the coding, right? So as you go from 1 to 2, right, from dog to cat, which is 1 to 2, there's a negative sign, which means happiness is, being happy is coded as 1. Right? So are you happy? Yes, no. Yes is 1, and no is 0. So as you go from 1 to 2, right, it goes from 0 to 1, which means it goes to being unhappy, which means a negative dog and being unhappy. Or you could say there's a positive relationship between dog and being happy. This will be a little clearer on. Now here's the really interesting part. The EXP, the exponent beta, in other words, this is the odds ratio. This is what we've been waiting to see. Right? So we don't consider the first odds ratio, the 1.39, because it's statistically not significant. Right? Now, the next one is a little unbelievable. Right? So you have to remember our sample, we had 100 people, and it was almost a third in each educational group. So the reference group is 30, around 33, and the college and graduate school are each around 33. So it's basically like 33 people compared to 33 people. So it's a small sample. And sometimes with small samples, you get really big effect size estimates. That being said, our effect size estimate for the graduate school, you see, is 23.85. So what that's saying is that people with a graduate school level education are 23.85, almost 24 times more likely to be happy in reference to people with a high school level education. So that sounds really big. And another way you know the finding is rather unstable is when you look at the 95% confidence interval to the right. So that's basically saying that the computer isn't, so we know that 23.85 is probably not the odds ratio among the population, right? So we have a sample, and the sample probably doesn't have the exact odds ratio as the population, but we're 95% confident that the actual odds ratio is between this number and that number. And the wider the interval, the less stable the finding. And you can see the interval here goes from 4.19 to way over 130. So that's a huge interval. So it's saying that the interval could be on the medium side. So the actual odds ratio could be like 4 times more likely to be happy, or it could be over 130 times more likely to be happy. So basically what it's saying is it's not really sure what to think, right? And like I said, it's a small sample, so we have to regard that finding with a grain of salt. Another thing to note is income level. Now remember, income is continuous. It's a continuous predictor. And in a binary logistic regression, you can't interpret the odds ratio the same way in terms of being more or less likely, like the categorical predictors. So you could report the odds ratio of 1.04, but it's not interpreted in the same way. Now our independent variable, our variable of interest, whenever you have a relationship, the odds is below 1, which makes it kind of tough to interpret. Right? So we're going to convert it. But before we do that, you'll notice that in the significant findings, right, such as do you live with a dog or a cat, the number 1 is not included within the 95% confidence interval. Now 1 is known as the null value in this interval. So if it's 1, that means there's no relationship, right? So you'll find when there's a statistically significant finding, 1 is not included. And when you get a finding that's like 0.06, right about statistically significant, it's usually at 1.01 or 1 is almost or just included. It's important to keep in mind. Now, let's convert that odds ratio so we can interpret what our independent variables test. So, is divide 1 by odds ratio, just kind of reversing it out. If you divide 1 by 0.105, which is our odds ratio, you get 9.55. And so this makes it a little more interpretable. So you can also do this if you change the coding. You would find, initially we had dog as 1 and cat as 2, but if we made cat 1 and dog 2, we changed the coding, you would also get the same conversion. Right? So you see here, when cat is made 1 and dog is 2, the odds ratio now is 9.55 in the actual output. Right? So what does that all mean? So the multivariate model indicated, again, wrapping it all up, while controlling for education and income level, analysis indicated a statistically significant finding, right? That's our first dimension, right? You see our box, D1 again, where those that live with a dog are almost 10 times more likely to be happy relative to those that live with a cat, right? So there you have your D3, the 10 times, that's our effect size, and our 2 D's, which are indicating our directionality. So as I alluded to before, we accomplished a lot at this point. Right? So what have we done? Just our most recent stuff, right? We used statistical analysis, right, the bivariate analysis, to identify the significant influences on our dependent variables. And then, 2, we used multivariate analysis to control for those significant influences and note the relationship between the independent and dependent variable, which is the relationship of interest. Then we identified at the multivariate level if there's a significant relationship between the independent and dependent variable, including the directionality, so significant in what direction does it go, as well as the effect size of those relationships within the context of that full model. And so this is kind of the apex of our statistical analysis, right? This is what we wanted to achieve. This is telling us what we wanted to know. It answers our hypotheses, and it answers our research questions. Now our next step is to communicate these findings to the world, right? So now we have the findings, but at this point you get almost sort of a gagged feeling because you have these findings, but you're the only one that sort of knows it. But you want to communicate these findings. Can you do it? Well, we can, because next week we're going to look at the write-up and report. discuss the scientific language, right, the order to present it, and the scientific language used to express what we did and what we found. We're also going to, not only express our findings, but we're going to express all the checks of data integrity, everything that convinces the reader that these are solid findings that were approached very carefully with as much diligence as humanly possible. Right, so that's next week. For this week, I just want to say thank you for watching the webinar, and please email any questions.